Okay, you're looking at this now. Okay, get your computer or get your calculator into stat mode because we're going to experiment with something right now. Let's see, are you seeing this? Yes, you are. So let's do something practical. Again, this could be your project. Steal this idea. If I would recommend, I hope you're actually already on, the move on this because as I said before, we should have some time the last few days for you to kind of work on it where I can help you and look at what you're doing and so forth, give you a little bit of advice, but.
I have a question really quick about that.
Yeah.
Does it need to be a binomial distribution?
Oh, not at all.
Okay.
No. It can be kind of anything we studied. So it could be, again, the two main things you want to think about is, what question is it you're just curious about? And then is the answer to that question a percent, which is really what chapter 8.2 and 9.1 were about, or is it a number, which is really what 8.1 and 9.2 are about. And so we're finishing up 9.2. So today's question is, in a practical sense, I wonder how much a cashew weighs. Now that's interesting, I guess, because there's obviously some big ones and some small ones. I was going to do M&Ms, but I was thinking those come from the factory and they're probably stamped out of the exact same mold and they're probably really close. But I have, cashews are awesome. And I had one the other day, it was gigantic. And so, maybe that's your interesting question. Super easy. If you can scrounge up a scale, borrow mine. Take your own measurements. All you need to do is weigh 30 of them and then you can answer that question. Of course, that probably would be interesting to somebody in that business. But again, are you the kind of person that can provide something to that business now based on your statistical calculation ability? I mean, this is an introductory kind of a course, but that's kind of cool. So let's do this. So if you're in stat, you can either write these down and enter them in your calculator or just enter them right now, up to you. So I have my faithful drug scale here, freebie. That was the old Doug. So, and this is in grams. You probably can't see it, but up in the upper right-hand corner, there's a little G, and so I won't bother to put it in ounces or something like that. Grams are a smaller measurement, so we'll get kind of a bigger number, be a little easier to work with. And I also haven't decided how many of these are we going to do, and so it seems to be settling on 3.3. So call the first one 3.3. That one's gone. Next one, 3.2. So far, if we stopped right now, would you agree that you'd kind of say, well, hey, cool. There's not a lot of standard deviation. There's not a lot of deviation between these. And in one respect right now, we might say, oh yeah, they're all about the same. It's about 3.2, 3.3, whatever, we're done. But maybe that's not the case. Maybe there is more variation. That furthers our thought, our third point now, 3.4, that kind of they're all the same. Does it make sense that I have to be careful to do this randomly? Like I can't look in here and, oh, there's a big one. You see what I'm saying? I just got to grab one, right? It's got to be a random sample. I just grabbed this one and it looked smaller and it really is. And so this is the first time we got 1.9, where now we're thinking, oh, whoa. So I guess maybe there is more variation. You might say the first three we got lucky, unlucky. I don't know what we got. So now all of a sudden we're thinking, there's some standard deviation here. Again, I'm grabbing these randomly. 2.7. Oops. Jump to 2.8, but we'll leave it 2.7. That's fine. And then the other thing is, obviously, I'm picking full ones. I'm not picking any halves. Another 2.7. 2.8. Do you have a sense of the fact that if this is an important question to us, we got to do this quite a few times? On your final project, I said, well, you need to have 30 of them. 3.1 for the next one. Can you tell without counting by looking at your calculator what you're on? Like at the bottom, I'm in a blank spot now, ready for the next one. It says L19, which means I'm about to enter the 9th number. So we have 8 of them right now. Does that make sense? That's just kind of cool to be able to notice. Another random one, 3. So there is some variation, and all of a sudden that one small one looks really tiny right now, although this one's pretty tiny as well. It's only 2.2. Again, I'm just grabbing these randomly, 2.7. Interestingly, notice those first 3, 3.3, 3.2, 3.4, those were actually really large and we didn't know it. You see what I'm saying? Like that's the point of what we're studying right now. If we'd have stopped with those first 3, we would have concluded the average is about 3.3 and we would have been done, but we didn't realize it. But our little sample of 3 was actually kind of high, based on the other numbers we got. You see what I'm saying? That's exactly why we're studying this. And again, I'm grabbing these randomly. I'm not purposely trying to make that happen. I'm just picking them out of here. So there's variation sample to sample. 3.2, there's one that kind of gets back up to the previous numbers. Kind of in that vicinity. We don't need to do a lot of these. I'll do a few more. 2.6. The one before that was 3.2. And this one's 2.6. I'll stick my calculator up there in a second. 2.4. And it looks to me, are you on the 15th one? So I'll put one more up there and then we'll have 15 and then awesome. 2.4, that's our last one. I don't really see any super tiny ones in here, but there's a couple tiny ones I could have thrown up there, but I'm not trying to skew the data. So just to check both me and you, because I could just as likely be wrong as you, this is what I got. That's what I have typed in. Is that what you have? And actually, you can't see the top. You see how the top one is 2.7? There's other ones up there, and you just can't see them. Of course, it's no big deal if one of us typed one of them in wrong, but the point is we're kind of nearing the end of this class. You have a lot of stuff you can do now with these numbers. Does it make sense as far as your final project? You could do a 5-number summary, which basically is breaking them into quarters and saying what are the smallest 25% of weights, what are the biggest 25% of weights, and what are the middle 25% of weights, and it gives us weights in there. So let's do one variable statistics on us. Your calculator tells you almost every interesting calculation that you'd want to know. So I say second quit, second stat, nope, not second, just stat, go over to calculate, one variable stats. And it says, fortunately, list 1, which is where all my data is. Let's just agree that we all got the same thing here. Again, I might be wrong too. Did you get what I got for the standard, for the mean up there, 2.77 approximately? So just to slow down a second as you're getting ready for your final project, that top one, I guess I can't kind of select those so you can look at them, but of course X bar is important. I would say the sum of all of those X's isn't very important. Do you agree with that? That's what you would have to do if you got the mean. You'd have to add them all up. Apparently the answer to that is 41.6 and then divide by 15, and that's where that 2.77 would come from. But I don't need to add them all up because the only number I really needed is the 2.77. And then the sum of the squares, that's kind of weird. We don't need that. And then of course these next two, which one are we using? You need to know this or you're blowing it. Which one should we be using? The top one, because we did not check all of them. We can't say this is the population of all. However, notice how close they are. It's almost like, well, one's 0.43, one's 0.41. That's not that big of a difference. And that's because we checked with 15 of them. That's a reasonable number of them. So they're not that far off anyway. I still don't think everybody has this down, but what does that 0.43 mean? You should have this down. But again, it's kind of a hard concept. You should say, okay, yeah, the average is, I'll call it 2.8. The average weight is 2.8 grams, and it's not weird to vary from that by 0.4 grams. And then when I think about it, I think, yeah, 2.8 plus 0.4, yeah, that's 3.2. Yeah, we got some of those. And then 2.8 minus 0.4 would be 2.4. Yeah, we got some of those. And so it was very typical, you would say, to vary by 0.4 from 2.8. And then you even know that it'd be unusual to go 2 standard deviations above and below that.
On the final project, you said that you could do a 5-number summary. Does that mean that you don't require all of those options that you give to be shown in the final project?
Yeah.
Oh, so
And-
you can choose out of them?
No, you should do the 5-number summary.
Okay, that's what I was, you said you can, but
You should. Now, let's stare at this for a second. Can you interpret that? Again, it's cool that the machine just gave this to me. What it means is if I handed you your cashew and it weighed between 1.9 and 2.4, you would go, bummer, I got the smallest quarter. That's the division. Anything below 2.4 grams is the smallest 25%. It's like the lowest fourth. It's the 25th percentile. I got one of the small ones. You understand that's what it's telling you? Do you see it takes 5 numbers to make 4 sections? So between 1.9 and 2.4 is the smallest 25%. Notice how that's 0.5 apart because we did have one that was really tiny. But notice the next category, sort of the next 25% is only separated by 0.3, 2.4 to 2.7. And then the upper half of the top, I guess the third 25% is between 2.3 and 3.2. And then the heaviest quarter of them was between 3.2 and 3.4. So again, as it turns out, those first 3 that we measured were actually really heavy. They were actually all in the top 25%. They were the biggest ones. Wow, that's kind of cool. And so now if you get one, does it make sense you know exactly where you belong relative to other people, where your cashew belongs relative to other ones? That's the idea here. Now you have these divisions that kind of roughly tell you what's going on. And notice that's it. There's no more calculations. That tells you all the basics. So write down, all we're really needing here is the mean and the standard deviation. So write those 2 down and then let's switch gears and do what we're doing right now. So, yeah, let's go to 2 decimals. If nobody says anything, it's up to you, but 2 sounds good. So 9.2. It'd be a big mistake on your final project to say 2.77. You should say 2.77 grams. That'd be really important. You're communicating nothing if you leave that unit off. And the standard deviation we got was 0.43. Again, approximately 0.43 grams. Now, we didn't do this, but back with the 5-number summary a second ago, remember how outliers are established? One way is doing Q1 minus Q3. I mean, don't you find yourself thinking, I kind of forgot that, I have to look that up on my notes. But it would be very good to report if any of those were outliers. You should talk about that. That would not be using all the skills you have in this class to not say something about that. I could do the mean plus 3 standard deviations. That was another method for outliers, right? Or I'll just write this down because I just think it's important for you. It's a mistake for you to leave this class not knowing how to do this. We know that unusual is the mean plus or minus 2 standard deviations. Notice I use the other symbol for standard deviation. So if I take the time to figure that out, that would be, I guess, X's individual. Remember, the variable here is how much does it weigh? And again, in this case, there's variation. They're not all the same. So if I add 2.43s to 2.77, I get 3.63. If I subtract it, I get 1.91. So anything outside of that range would be unusual. Now, if I look back at my calculator, again, notice we put them in not in order. Excuse me. So therefore, if we had a really big list, like 40 of them, does it make sense? It'd be actually kind of hard to find any of them. So that's why there is actually a sort button on your calculator. But again, that's why Excel is a little better, because you would want to sort this list. So it's really easy to find the smallest one and the largest one. Did we have any that were unusually small? I remember we had that one. Was it less than 1.91? I can't remember what it was. I'm going to edit right now to look. Yeah, 1.9. We had a 1.9, and that is less than 1.91. So, you know, if that was the one you got, you could say, man, that's a ripoff. Mine is unusually small. Not crazy. Remember, 5% of them would fall in that category. This represents, as you know from the empirical rule, 95% of the cashews. So 5% is 1 in 20. So although it's unusual to get 1.9, it's that doesn't mean it's crazy. It's not an outlier. But I'd be bummed. If that was mine, I'd be bummed. No, man, mine's unusually small. I don't think we had any over 3.6. It seemed like that early one, 3.4, was our biggest one, wasn't it? Yeah, it was. So we had one that was unusually small. Like, these are cool things to be able to say. Before, it was just a list and you didn't know anything of what to do with that. Nothing intelligent to say about it. And now you know quite a bit. Again, all of that is the stuff we've been studying this term. What does 9.2 add to this discussion, though? With a confidence interval. Is that something you could put into words? What else can I do with this that's kind of cool? What is my ultimate goal here? What was my original question? Yeah, don't I actually want to know? Kind of my original question is really this, isn't it? Again, that's the symbols of this class, but I would actually like to know the average weight. The actual average weight, not the sample. I only checked 15 of them. That could have been a weird can, a weird farm, who knows, a weird factory, who knows. But I really would like to know what the population mean is. And all I have is kind of what I have to work with. And that's not bad. I did check with 15 of them, but there's going to be error associated with this. I only checked with 15 of them. Remember, part of the error could be you doing a bad job of your study and sorting through them. It's not random. You sorted through them, picked all the big ones. But there's going to be error in this. As I said, as I hope you understand, we did N is 15 for our study. And if we went and did this again with 15 more cashews, or even a totally different number, it doesn't matter. We're probably not going to get 2.77. So there is an actual population answer to this, but we'll never know it. And the actual answer is out there. We'll never know it. But when we do a study like we just did, our answer might land here, sort of X1 bar, our first trial. Somebody else does one that lands here, X2 bar. Somebody else does one that lands here. And eventually you get enough of these. Maybe even somebody gets a really tiny one like this one down here. And remember, they don't know it until they talk to the other 3 people and realize, wow, mine was really low. I wonder what happened there. But if we did hundreds and hundreds of these, what ends up at the middle of this distribution of all these little miniature studies, what ends up right there? Yeah, the actual answer we are after. So that's kind of cool to think about. And so because that's normally distributed, then we can take a guess at error based on the formulas that we looked at. So what do we do with 9.2? Well, first you have to say how confident you want to be. Again, in the real world, you get to pick that. It's a percentage. Do you want to be 98% confident because this is really important? Or you're like, let's chill out a little bit. Let's make it 94% confident, something like that. Let's produce And I want you to do this ahead of me. I'm going to give you enough time to do this yourself. A 94% confidence interval. Can you make it? And more importantly, do you even know what you just made? And I see lots of you guys on Zoom too. Feel free to speak up. I think I'll be able to hear you. So don't feel like you can't participate, ask questions. The best answer we have right now for the population mean is 2.77 grams for the average. Our question of interest here is a number, not a percent. But we recognize that there's error in this study, so we mathematically produce that error. So the recipe for error calls for 2 ingredients. We're using the T distribution, not the normal, although they're roughly the same. Slightly different equation that we don't need to know. That's one of our ingredients. The other one is the new and improved standard deviation.
I'm curious how you differentiate use the distribution, like with the wording of the question.
Yeah, as far as the test is concerned, you could definitely ask me that, but I would say something like produce a 94% confidence interval for the population mean is probably the way I would say it. Because remember that 2.77 is not true, and it's better than nothing. We did do a study, but when you produce a confidence interval, you're saying, I think it's 2.77, but based on the error in this study, it could be off by 0.5 grams or 0.6 grams or whatever, and that's what we're trying to calculate right now. Remember, this E stands for error, or sometimes your book will say margin of error. And again, that's just reflecting the fact that, as I showed in the blue graph a second ago, that if 5 of us go out there and do these samples, we're not all going to come back with the same answers. So we're going to differ from each other. So the t-score, kind of like the z-score, comes from inverse t. What do you type in though for the percent? A little louder, what?
0.97.
Very good, 0.97. The middle percent of this, 94% of these blue studies we did earlier, 94% of them are going to fall inside or close to the actual answer. The problem is we don't know which direction ours landed. Well, if that's the case, then there's a 6% chance, and this will be important in the next section, The error in that is 6%. In other words, we have a 6% chance that unfortunately our 2.77 isn't even in there. It was like a really low one or a really high one. But we feel like that's pretty low. It's only a 6% chance that I screw this up. But as the little formula shows, I got to cut that in half for the two tails. So that leaves 3% for the left and 3% for the right. And then what we'd really like here is this t-score or z-score, and that comes from the area to the left. As Hannah said, that'd be 94% plus 3%. So typing 97% in here will give you the positive answer for that z-score. As I said, out of laziness, you could have just put 3% in there, and that would give you the negative answer. And then oddly, inverse T asks for the area to the left and the degrees of freedom. What's the degrees of freedom in this case? N minus 1, so it'd be 14. So I'm doing this with you now, second distribution. Hopefully I'm catching up to you here and you're fixing any mistakes in your understanding as we go. And I got a z-score of, not surprisingly, 2.05. I'm rounding it off. Why do I say not surprisingly? Well, earlier in this class, didn't we say that 95% was a z-score of 2? I mean, isn't that what we just did a second ago? 95%, you go 2 standard deviations above the mean. So this is pretty close. So therefore, we're roughly 2 standard deviations above the mean. Now, again, the t-score gives a slightly different answer to that, but that's that score. Secondly, and finally, do you understand this one? Do you understand that this is the standard deviation here, nut to nut to nut, from the mean that we got? So it's not weird at all for one nut to be 0.43 bigger or smaller than 2.77. What is this modification of that? In other words, I get to say 0.43 over here. But why am I dividing by the square root of n? What standard deviation? It's still a standard deviation, but what standard deviation is that? Again, I think this is hard to get your mind around, which is why I'm asking about it. Yeah, it's the standard deviation of my sample from the mean. Now remember, my sample was built of 15 nuts, and so it's not going to be as far off as one nut would have been. Remember, we did the first nut and it was like 3.4. I mean, it's off by a mile. So this is the standard deviation sample to sample to sample. Well, that's not going to be as much because 15 nuts are going to keep anything weird from happening. We did have one unusually small nut, right? But there were 14 other nuts to kind of balance it out, making it not kind of screw the data up. So I get roughly 0.11 for that. So there's my 2 ingredients. So now I can say error is equal to our t-score of 2.05 times our standard deviation and I got 0.225. So that 5 would cause this to round up to a 3. And again, this would be a good place to not be lazy anymore and actually stick the grams back in here. And again, what is that error from? It's telling us about our 2.77. It's saying, I would not be surprised at all. There's a 94% chance that now we can say something about our mean, and that is, hey, it's only off by 0.23 grams. So it could be as high as, I guess that's 3. So remember, there's 2 ways to list the confidence interval. You either say, let's see, is this the way to say it? You say, I think the population mean is actually 2.77 plus or minus 0.23. Maybe you list grams over here, or you go ahead and list what your book calls the interval of that. If I add 0.23 to that, I end up getting exactly 3 grams. If I subtract 0.23, I get 2.54. So that's actually listing the confidence interval. Again, do you see this as like an improvement over what we said before? before we went to the world and said the average weight of a cashew is 2.77 grams, but we didn't tell them we only checked with 15 of them. Now that we sort of are honest and checked with just 15 of them, now we're saying there's, when you do studies of 15, 94% of them will fall inside there somewhere. So again, what it means is the average weight could be as low as 2.54, or it could be as high as 3. Because we realize there's error in our study. We realize we did one study and it's not perfectly going to land on the population mean. And so this is an improvement because we're sort of admitting something about error. Now, new thing. What if you decided that error is kind of too big? Like you got here and you went, that's kind of disappointing. It's too big of an error. I work for the Cashew Society, and like this is my whole job, and I want to have a way smaller error. So we were kind of stuck with all of that, right? Like we just randomly did 15 and then we had no choices. The error just came out what it is. And now we say, well, darn, that seems kind of large. We did the same thing with percentages. Oh man, that one time we had a 17% error or something. And it feels like, gosh, we didn't learn anything from that study. So what if you said 0.23 is too much error? You didn't like that. And you sort of said, I wish, or I want error to be way smaller. So let's make it something like, I don't know, 0.07 grams. Notice that's like a third. If that had been 21 divided by 3 is 7. So this is like a third of the error. We only want to be off by 0.07 grams. We're disappointed in that. Do we have any control? Is there anything we could do with this second question? Take a look at your note sheet. And let me clean it up a little bit from last time. So we just got done. So the thing I'm worried about on the test, where there's percents together, and notice I highlighted this, is can you tell which formula to use? And that's why I kind of highlighted percent or mean. Which formula do you use? Well, is the question at hand a percent or is it a mean? Ours is a mean. So we used this formula. Cool. And we found our error. Awesome. But now look at this formula. Just like for percents, we had a way of recalculating n. In other words, how many cashews should we have weighed? The fact that I weighed 15 is what was the major contributor in having a 0.23 gram error. And I put no thought into that. I just got tired of weighing them and stopped. So if you, and I hope this just feels natural to you, if you had checked a lot more cashews to get your 2.77, that would have made it a heftier, more solid kind of a number. The less you check, the more room for error there is. And so does this formula speak to you? What's its ingredients? Again, it's a recipe. I can calculate n. In other words, that's the one thing you actually have control over, is I could have checked with more, or I could go back now and just rerun the experiment and get a different n. But notice what it's calling for. Let's see, it's calling for an error. That's the error we just wish we had. We just made that up. And again, the second question, to kind of Hannah's point, like what might that look like on a test? I would say something like, suppose you weren't happy with the error that you got in the previous question and you wanted an error of 0.07. And then I would say something like, how many cashews would you need to weigh in order to get that error? And so you'd come down here and put in your 0.07. And what's that represent right there? Yeah, that's the standard deviation you calculated earlier. Notice it's not S over the square root of n, it's just S, so that's the 0.43. And then here's something that's kind of interesting. I thought when we were in this section, we were using T scores. Did that stand out to you? I thought we were using T down here. And then all of a sudden this one is saying use Z. Is that like a typo? Did I screw that up? The answer is no, because what does a, let me take a picture of this. What does a T score require? Like a second ago when we found T of alpha over 2, we put a percent in, and what was the next thing we put in? Degree of freedom, which actually depended on n. In other words, because we knew n was 15, we were able to stick in the degrees of freedom of 14, but notice here we don't know what n is. The whole point of this formula is to find n. So we basically have to just use the normal distribution, even though it doesn't fit quite as good. That's kind of the logic of this. So let's go use that. See if we can get an answer. So this recipe, unlike air a second ago, calls for 3 ingredients. And so we said, okay, cool, the air here, the new air. And you should appreciate that that could be confusing, right? Because don't we have 2 E's now? We have 0.23. And so that's why I would word the question in a way that helps you a little bit. I would say something like, suppose you're not happy with your air of 0.23 and you wanted a better air of 0.07. Does it make sense why we're using 0.07 here if you think about it? If you don't think about it, and this doesn't make sense to you, I can see somebody getting confused, like, oh man, which one do I use? And our S was 0.43, if I remember right. And lastly, our Z score. So our Z score of alpha over 2. Well, if we're sticking with, so we're using the normal distribution now. If we're sticking with 94%, then this percentage to the left hasn't changed. The only difference with inverse normal is it asks for the mean and the standard deviation. And because we're talking about a Z-score, which is cleansed of its mean and standard deviation, that's what we type in. Now that's the same thing we just did a minute ago for inverse T, except for we get a slightly different answer. A second ago with inverse T, when we did that, we got 2.05. We're going to get a slightly different answer for this. You might do this with me. I got 1.88. So again, just for those of you that are tracking with this deep enough to make sense of it, I said before that when you have a small sample, this is what that researcher discovered that I mentioned, Gosner or something like that was his name. He discovered there's actually more variation when you have a really small data set, and 15 is kind of pushing that. That's a pretty small data set. So therefore, the T produced the answer 2.05 for this, which is a kind of a much bigger answer than the Z-score produced. That's why he made this. So he found a new equation that basically was a little bit wider and it produced a larger answer, and it sort of seemed to fit the real data a little bit better. Okay, ingredients are found. Hopefully now you speak the language of algebra, that you're not intimidated by that formula. That you say, oh yeah, that's just order of operations. So you're saying n equals the Z-score times the standard deviation divided by E. And it'd be really easy to get all that stuff typed in and kind of forget there was a squared there. And again, you're lucky you have a graphing calculator. You don't have to type these one at a time. You could type that whole disaster in your calculator right now and it'll just tell you the answer. Now, because we were trying to get a lower error, does it make sense our n is going to be higher than 15? We did 15 a minute ago and we got an error of 0.23 grams. With this, we're probably going to get a higher n. And of course, we're sort of hoping and maybe it's like 80 and not 8,600 or something like that. Like you could choose a really small error and it'd be really costly. It take a lot of time. So parentheses 1.88 times 0.43, you can just type right what it says, divided by 0.07. And that is squared. I got 133. Now think about this carefully. 133.36. Your assignment, fortunately, I think tells you what to do, because obviously you can't weigh 133.36 nuts. So should you do 133 or 134? The honest answer is like, who cares? Pick one, because you're going to have an error of around 7%. If you choose 133, your error will be a hair above 7%. If you choose 134, it'll be a hair below. So fortunately, I think in your assignment, they tell you, as they kind of should, you should probably round this number up. Even if, like this one, it should round off to be 133. It's actually better to round it up, because then that'll mean your error is, well, a hair better. You said you wanted it to be 7%. Well, you don't want it to be higher than that, even if it's a hair higher. So I will add the note here, even if it doesn't say this in my open math, but rounding up is actually best. So you would report, cool, you didn't weigh enough of these things. Go back and weigh 133 of them, 134 of them, and then you'll get a much more satisfying error. Little side note that's just interesting. What if you wanted the error to be really small, like 0.02 grams? All I have to do is retype this exact same formula, but just put 0.02 right there, all right? That's what I'm doing right now. If you wanted that small of an error, you get 1,634 for N. It's like that was an expensive choice. Do you see what I'm saying? Oh, now I'm going to be here all day weighing stupid cashew nuts, right? However, isn't it kind of cool? I mean, if this was for the industry, if this wasn't for the entire industry of cashews and you were being paid for it, that's not terrible, 1,600. And now you can actually say, I'm really confident. I'm really confident in what the population mean is. Do you see how that's a cool addition? Do you see how what we just did there at the end is actually a pretty natural thing to do? Don't just be stuck with whatever error happens. Use that formula to get a better answer. That's kind of cool. As my dad used to say, how does that grab you? Are you tracking with that? You find yourself, there's two things I'm after. One of them is I can push all the buttons and get the same answers you're getting. And I think I can memorize that long enough to spit it back on a test. But I'm a little worried because we had a set of formulas for percent questions and we have a set of formulas for mean, and I might just fumble that all up and jumble it up and fail the test. I'm concerned about that. But I'm actually more concerned if you study enough to where you can keep that stuff straight on the test. I'm actually more concerned that you see how cool this is, that you see this is now an employable skill. We're actually done right now with what people want you to get out of this class. Like if we quit right now, there isn't any of your whoever's wanting you to be here, nursing or whatever, they don't need you to know chapter 10. But can you see this as employable? Can you see that if you could demonstrate that to somebody? As I said, I think it would be smart of you to do something like this in Excel and make it look really cool. Not just so you don't feel silly in front of everybody else, although maybe that's a motivation too, but because wouldn't that be cool to show somebody, hey, look the stuff I learned in statistics. It's not just, yeah, I sat there and got a B, but if they were to ask you some questions about it, you'd start fumbling around and sort of, oh, I don't really know anything. That's the way I'm with history. You took history and got an A. Cool, what'd you learn? You know, it was like 6 months ago. I could talk for 5 minutes maybe. I mean, that's kind of sad. I sat in that class for 11 weeks and I have 5 minutes of things to say about what I learned. I mean, whose fault is that? Mine, because I can't just sit there passively listening. I got to put some energy into this. This is hard. There's a lot of formulas here. You could totally screw this up on a test. I mean, you probably feel that, right? But if you study, put your own time into this and kind of make sense of this, I think you can see that producing something on your final project and, you know, making your own set of notes about things that you need to remember to keep straight, those kinds of things. Being able to display to somebody who's trying to hire you a set of skills right here that you can actually go perform this. And again, what I think I just did is neat, which is why I even took the time to weigh the cashews instead of just giving you a list like an assignment would do, is we started from nothing. And now we have a pretty good answer. If we took the time to go re-weigh 134 of them, now we'd, for one, we certainly would get a slightly different answer than 2.77 because it's just a different study. And we wouldn't get an error of 0.23, we'd get an error of around 0.07. And now we'd be sort of a lot more confident. We'd have a lot tighter of an answer as to what the actual population mean is. And there would be people that would be interested to know that, I think. A very small select people that sell these for a living or something. Do you have questions for me? Is this something you just feel like, yeah, I just need to go alone in a room now and stare at these things and try to assimilate it? One of the things I would encourage you to do, because I might do one more quick example, but I'd like to give you some time today to, again, go work on my open math. We're doing a lab tomorrow, and we're kind of a little bit of a day ahead on the schedule, but our last lab we're going to do tomorrow where we just get Excel to do all this. Because you can't appreciate that although this calculator is cool, it travels with me. I can put it in my pocket. I could just be talking to someone and get an answer. I can't display any of this. Does that make sense? So the ability just to get Excel to do the same thing will be cool. And I think that'll help you on your final project because you are trying to display it to somebody. So hopefully that'll just be more practice. Because you'll be working a lot on that tomorrow, and probably because tomorrow's only an hour, probably I'll even give you some time because we're a little bit ahead to even work on it a little bit into Wednesday before we start something else. I'll be able to walk around, which means you can ask me if you finish the 9.2 assignment tonight, minus the 2 or 3 things that threw you. Like Hannah said, maybe it's just the wording of the question, and I'll help you think through that. But the other could be just conceptual understanding about how to read the formula sheet and get different answers, and we can talk one-on-one about that. And certainly the Excel will help you. And I will ask you some kind of probing questions like this. Do you understand what you just calculated and so forth? Can you explain at least a little bit what's going on? Okay, so let's just perform one other one really quickly here. Except we'll gather this, and again, this would be an excellent final project. How many hours of sleep do you kind of get a night? Now that could be because you don't sleep well, or because you have a lot going on and you wish you could sleep 8 hours, but you can't because, you know, the alarm goes off, etc. So just answer it kind of lately, you know, approximately how many hours of sleep do you get a night, whoever's fault it is, your own because you don't sleep well, or your job, or whatever the case may be. But I'm just going to go around the room. There's not that many of us, so we'll do everybody in here. And this won't be a good sample. Do you understand that? Because it's a small room. You guys online, they're watching on Zoom, type it in the chat and we'll throw your data in there too.
This is literally what I was going to do for my class.
Sweet. Good. It's a great idea. It's just numbers. I mean, if I told you back here, this was hours of sleep, does that change anything we did? You understand what she's saying though? She's like, I don't want to, which I compliment you for. You're thinking, it's like, I don't want to see this because this is what I'm about to do. But what are we really going to do here? We're just going to get a list of numbers and do all the same calculations. It's just a question of what label is attached to them. Perhaps though, just what we ask in this room will, and that's what's kind of cool about this is if you change topics, it doesn't really change anything we just did. All I'm going to do here though is just write down the right answer, and we'll spend like 5 minutes, and hopefully you can kind of buzz through the same thing we just did fairly quickly, and then just check to see if you got the same thing I got. Then I'm going to shut up and turn you loose. And if you got it wrong, I want to come around and talk to you about why you got it wrong. Having said that, If you're like, I still don't want to watch this,
Well, I just don't
then
want to seem like,
don't.
like when you see like.
Right.
I'm not stealing it from this.
Yeah, absolutely.
My idea.
I love it. I totally get that. But again, I was encouraging you to steal it because these are sometimes hard ideas to come up with. So, and I would say this one is probably more valuable than the nut one, right? Because it kind of affects people. And maybe you're not sleeping that well and it's like, well, how bad is it? Am I like an outlier low? Am I unusually low? Like maybe I should actually go get checked. You see how this information would be important to understand. So yeah, good on you. Is that what you want to see? Okay, so who was that? I just wasn't looking at, was that Alessandra that weighed in there? Was it? So he said 9 hours a night. And it's kind of funny, but I sort of, and I'll move that back up so you can see it again. I think he said 9, didn't he? Yeah, 9. So I have 8 in my head as like the right answer to this question. You're supposed to get 8. I listened to a really interesting podcast talking about this because some people kind of panic, like, oh my God, I'm what is it called? What do you call it if you can't sleep? Insomnia. I'm an insomniac. I have insomnia. Like it's a disease, and they start panicking. He was just kind of talking about that. What are you, Hannah? 7. Keep going. 10. Go ahead. Who's up?
8.
8. What are you? Rest of you, give me your answers. What's yours? 7? 6. I'm going to say 7 for me. What are you? 8. Okay. So there's your data. Notice I called them X because did we all say the same answer? We did not. That's why it's X. It's a variable. We get a different answer for this. It looks like N is 8 here. Does that feel low to you? Does it feel like a bad study? Like this isn't going to be all that great. We're going to get kind of a large error. So 2 things I want you to calculate. You begin calculating this right now, but one of them is a 90, let's make it a little bit weird decimal, a 97% confidence interval for this. And 2, find N if, so we're going to have a pretty big error here. Does that make sense? Because N is so small, we're going to kind of have a large error. Remember, what we're after is the average answer to this question, because as soon as I know that, then I'm immediately going to know am I above average or below average, and I'd kind of like to know that. So second one is find N if you want the error to only be 15 minutes, but we're measuring in hours, so I'm going to make up a pretty small error. So all I want to do is just put the right answers up and then come around and talk if you got it wrong. maybe I went too fast and made a mistake. That's not impossible, but I think I have the correct answers up there now. So ask me questions. You guys online too, chime in. As far as your final project, these two questions, I think, illustrate, but you should understand that one of them you could do yourself, like borrow my scale and weigh something, or maybe you have a scale and weigh something or whatever. A bowling ball, you can gather it yourself and then you're done. This one, however, would require you to ask people, right? Which you can do on Facebook. And again, we said it's kind of important to note that because you're asking, well, people that are connected to you, that's probably not the best way to do it. And I don't want you to go to the trouble of making this random and like standing on the street corner, those kinds of things. Just collecting where you can, note the limitations of what you did. It's like it makes it more fun if you gather your own data, but I don't care. You can steal it offline somewhere if you want to. The other thing that's interesting about this particular topic is you probably could Google search this, but still get some issues with people. You could probably find out a bunch of information about it. It'd be interesting to compare your own research to what you got. Now, I would assume online, though, they would have checked with hundreds of people. They have sleep studies. People do this for a living. There's whole people that their entire job is studying people's sleep and helping them fix it. So there's probably thousands of data. So I would assume what you found online, if it was credible, would be a better answer than what you're going to get if you're only going to check the 30. Right? At least it'd be kind of cool to see, yeah, the only difference is they got really good data. They don't have the data as much of it. Pretty good. Yep. So because you're doing a 97% confidence interval, you have to draw a picture of that to get the percent correct. Like what did we do before? If you get this right and you want to leave or start on my open math or something like that, do it, because I'm not going to say anything else. I just, if you can't get this question I just did, that's not good. Like I want to talk to you one-on-one until you do. Let's see what we did here. We said that was a 94% confidence interval. And we said, oh, okay, that would leave 6% as an error. So I'd have to put half up here and half down here. And because the T score, the Z score for this location requires area to the left, I had to add 0.94 and 0.03, which is why we entered 0.97 right here. So you got to do the same thing. It's just we used 97% was the middle. Think about that. Ask me questions. You're not going to tire me out. Bother me until you get this. This next test is not going to go well. Yes. Yeah, so you decided you wanted a smaller error. And of course, that's because in the one above, you got an error. I don't even know if I wrote it down, 1.23. So when I did this up here, I got the average is 7.75, but I got an alarmingly large error of 1.23 hours. So my reaction to that as a researcher or something would be like, man, my average is off by 1.23 hours. That seems terrible. You mean the actual right answer could be as high as 9 hours and as low as 6.5 hours? Yeah, that's exactly what it means. Why'd that happen? Because you checked with 8 people. So then I said, well, I don't want an error of 1.25 hours. I want an error of 1/4 of an hour, 15 minutes. Well, you're going to have to check with more people, but not crazy more. It's not 50,000. Again, I'm not 100% sure. I did it kind of fast, but I don't think I made a mistake, but I could have made a button pushing mistake. So you're using, you're back to using this. Just to haul some of that around. I have 0.7. What's that? Oh, let's see what it's doing.
Oh, sure, yeah.
Oh, you got some? Yeah. Yeah, let me see something. I'll listen if you want to, but Shelley's starting to look at the assignment. One of the first questions, a lot of the questions in your assignment ask is what's the parameter of interest? Now that's a confusing statement. That's an example of something you should read and go, whatever you're talking about. They're basically just saying, what are we talking about here? A percent or a mean? Is the question at hand a proportion? Or is the question at hand a mean? Today, the question at hand is what does it mean? Because you said how much does a nut weigh, and then how many hours of sleep. The question at hand was not a percent. Does that make sense? And the reason they're asking that is because you have 2 sets of formulas now. You have a percent set and a mean set. Now, because you're doing section 9.2, all of those questions are going to be a mean, but don't elaborate. Don't say much. It's just kind of saying, do you understand what set of formulas you should be looking at here? So state the parameter of interest. That's what it's getting at. What are we talking about here? Yeah, so the necessary, let's see, the necessary conditions. Remember how it was like